So everything we've done so far, we've dealt with finite sequences and series. So there are sequences and series that end. We know that there are 30 rows of bricks, so we know that we're looking at 5 generations of children. So you know that it ends. What we're going to look at today are infinite sequences and series. So ones that go on forever. And I really like this stuff because I think it has one question in particular we're going to do I think is really interesting. Because it's not what you anticipate to happen. So first let's talk about this. And this also will, not there. Yeah. Oh, okay. I'll have to check on that later. So this also I should tell you, today you begin to learn calculus. We're going to do some limits with this stuff. So limits are the basis of calculus. So they're in the pre-calc curriculum, but they're also what I start with in calculus. So we won't go nearly as in depth as I do in calculus, but this is the beginnings of calculus that we're starting with here. So if I have the sequence 1, 1/2, 1/3, 1/4, 1/5, that sequence is neither arithmetic nor geometric because you're not adding a set number each time. And you're not multiplying by a set number each time. You're adding 1 to the denominator each time, but that's not adding a set number, right? Because you're not adding it to the whole number. So if we wrote a formula for this, we could write a formula where our formula was something like this. I'm going to use this recursive notation, a sub n equals 1 over n, or you might see like y equals 1 over x. There. So if we wrote this formula, our first number is 1 over 1, our second number is 1 over 2, our third number is 1 over 3, right? So this would be a formula here. So as n approaches infinity, so as n gets bigger and bigger and bigger and bigger, what happens to the value of that a sub n? What happens to that? It gets smaller. What does it get closer to? Does it ever become negative? No. What? It's going to get closer and closer to 0, right? Because each fraction is just a little bit smaller than the one before. We've got 1 over 2, 1 over 3, 1 over 4, 1 over 5. All of those get a little bit closer to 0. Eventually, we're going to have things like 1 over 1,000, and 1 over 1,000,000, and 1 over a gazillion, which essentially is so tiny that for most cases it would really just be 0, right? Because unless you're really needing to be precise, 1 over a gazillion, if such thing exists, is really so close to 0 you don't need to, you would just call it 0. So as n approaches infinity, a sub n approaches 0. Okay? And this is a limit, and limits are a major part of calculus. So let me show you the notation that we use for this. Yes. The limit is like we're going towards infinity, but the limit is 0 because that value is never going to get below 0, right? So if the answer was infinity, you are correct that it really wouldn't be a limit because you're not going to go like you're not going to go on the highway and see a sign that says speed limit infinity, right? Because that would not be a limit because you could go as fast as you want. But here our answer is not infinity. We're looking at as we approach infinity, what is the limit? And the limit, you can't go any lower than 0. You're going to get closer and closer and closer to 0. So this one does have a limit, but we'll get into what you're talking about there. Like sometimes there are limits that do not exist. So the way we write this in calculus is like this. We'll put LIM, which means limit. And then because our variable here is n, we'll put n and an arrow and infinity. So that means n approaches infinity. And then you'll either see it written like this, you'll just see a sub n equals 0, or you may see it written like this, the limit as n approaches infinity of 1 over n equals 0. So that's the notation that we use for this. And we'll be seeing quite a bit of that over the next few days. So let's look at these limits. So the first one we've got here is the limit as x approaches infinity of 1 over x squared. So, like, if I think of making myself a chart for this, like if I had 1, 2, 3, 4, 5, 6, and of course it keep on going forever. If I had 1 over x squared, y would be 1 over 1 squared, which is just 1, right? And if I plugged in 2, what would I get? 1/4, 3, 1/9, 4, 1/16, 5 would be 1 over 25, 6 would be 1 over 36. So as x approaches infinity, as x gets bigger and bigger and bigger and bigger, what happens to my value of 1 over x squared? What? It gets smaller and closer to what number? 0. So this also equals 0. This really did the exact same thing the other problem was doing, except for it went to 0 quicker, right? Because that number in the bottom was squared. So rather than 2 being 1/2, I had 1/4, which is even smaller, right? And then 1/9 and 1/16. So, yeah. So the limit, it really doesn't make a difference whether it's 1 over x, or 1 over x squared, or 1 over x to the 5th, or 1 over x to the 1000th. It's all going to go to 0, right? This goes to 0 a little, or gets closer to 0 a little faster than the last problem. But as far as the limit goes, it's the same, right? What about number 2? We've got 20,000 over x. So if I made a chart for this, I'd have 1 would be 20,000, 2 would be 10,000, 3 would be, let's grab the calculator on that one. 20,000 divided by 3. 6.6, repeating. So my numbers are decreasing. Is this going to approach a number? Okay, Jonathan's saying 0. Right now it doesn't really look like it, right? But our numbers are decreasing, but eventually it's going to go really, really, really far out in that direction. So from the beginning here, it looks like you still got pretty big numbers. But eventually, you're going to have 20,000 divided by 20,000, which is going to give you 1, right? And then you'll have 20,000 divided by 1,000,000, which will be a fraction. And then 20,000 divided by 1,000,000,000 and 1,000,000,000,000. And eventually, this becomes a teeny tiny fraction, right? It takes a little longer to get there, but eventually it happens. So does it matter what number you have in the numerator here? No, because eventually it's going to reach 0, or going to approach 0, we should say. It never gets there because we can't actually get to infinity. So this answer would also be 0. Because eventually, when those numbers get really, really, really big, you're going to have small fractions that get closer and closer and closer to 0. So, some properties of limits that we need to know. And they're written for you there. If you have a number, and really this 1 right here, it could be 1 or any number. Okay? positive or negative. It doesn't matter if it's positive or negative. So if you have any number over a variable raised to a power, then, or any power, it could just be 1 over x, but it could be 1 over x squared, or it could be 25,000 over x to the 17th. Any of that, it's always going to approach 0, because that fraction is going to get smaller and smaller and smaller and smaller. So x's in your denominator make that limit become 0. Okay. Some other properties. If we have the limit of f of x plus or minus the limit of g of x, we could take those limits of f and g separately. So we could take the limit of f and add it to the limit of g. That should have a plus or minus sign right there. It works with subtraction as well. Same thing for multiplication. If we have the limit of f times g, we can take the limit of those separately. Limit of f times the limit of g. For division, it works. Limit of f divided by the limit of g. And then this last one is a little strange. It's the limit as x approaches infinity of c. And here c is some sort of integer. Right, so an example here would be like the limit as x approaches infinity of 7. Right? So as x gets bigger and bigger and bigger, 7 doesn't change because it doesn't have an x with it. Right? So the limit as x approaches infinity of 7 is 7. The only way it could be anything besides 7 is if you had an x involved, like 7 over x or 7x or 7x squared. But if it's just a number, the limit is that number. So if I had the limit as n approaches infinity of 5, what would that limit be? 5. What? Even with negatives, it's still the same. So like if this was a negative 5, your answer would be negative 5. Okay? So let's look at the next question. That's just so fuzzy. I copied and pasted it. So, alright, so the reason I phrased this one like this is because our textbook does this. It's telling you to find the limit as x approaches infinity of a sub n if, and then it gives you this list, 9 over 5, 16 over 4, 65 over 27, ... and it gives you the 7n squared plus 2 over 2n squared plus 3n. This is the part you need. This is just like if you wanted to try to figure it out on your own before they give you the formula, which you don't. So just use this formula. What it's asking is for you to find the limit as x, or I guess n approaches, that should be an n right there, n approaches infinity of 7n squared plus 2 over 2n squared plus 3n. So one thing we could do is we could type this into our calculator and just like go look at really big numbers, but sometimes that doesn't help very much. So let's do that here just to see if it helps us any. Because your whole test will be calculator active, so this is an option anytime you do this. So let's go to y equals, let's type in 7x squared plus 2 divided by 2x squared plus 3x. Okay, and if we go to the table, let's see, let me change my table back to normal. Go to the table. I get an error at 0 because I'll get a 0 and then it's on there. But as I go, looks like these numbers are getting bigger. It's really hard for me to tell where it may stop. What is a good idea for this is go back to your table set and maybe instead of counting by ones, count by maybe 100 or something like that. So if you go second window, that gets you to your table set menu. And now if you go back to your table, it'll count by 100. So if I do this, what does it look like it's getting close to? It's not getting past 3.5. Right? So just based on that, my best guess would be 3.5. Now, in this case, that's going to be a pretty good guess. In other cases, it may not approach infinity it may not actually start to get close to that number until way far out, like in the gazillions. So it might be hard to tell on your calculator. So let me show you another way that you can tell without your calculator. Okay? To solve algebraically, okay, so to do it without the calculator, divide everything by the highest exponent of the denominator. So what is the highest exponent we see in the denominator? The n squared, right? So we're going to divide everything by n squared. Everything in top and bottom we divide by n squared. So when we do that, we get the limit as n approaches infinity of, what do I get when I do 7n squared divided by n squared? Just 7, right? And then over here I'll get 2 over n squared. And then when I do 2n squared divided by n squared, I just get 2. And then 3n divided by n squared, one of those will cancel, so I'll get 3 over n. Now it looks like I just made things worse rather than better, but let me show you why this is helpful. Okay? The next thing we want to do is take each limit separately. Okay? And what I mean by that, those rules of limits told us if we are adding two things, we could take the limit of them separately. If we're dividing two things, we can take the limit of them separately, right? So I'm going to write this step, although when you do these problems, you're not going to write this step. That means I'm taking the limit as n approaches infinity of 7 plus the limit as n approaches infinity of 2 over n squared over the limit as n approaches infinity of 2 plus the limit as n approaches infinity of 3 over n. Right? You can do that part in your head. You don't necessarily need to write it, but it might help you see what I'm talking about here. So, what is the limit as n approaches infinity of 7? It is 7, right? What is the limit as n approaches infinity of 2 over n squared? Okay, it's going to be 0 because I've got that n in the denominator, which means I've got a number over a variable, and so that variable is going to get bigger and bigger and bigger while the 2 stays the same. 2 over 4, 2 over 9, 2 over 16, 2 over 25. It's going to approach 0. All right, anytime you got the variable in the denominator, it approaches 0. What's the limit as n approaches infinity of 2? 2. What's the limit as n approaches infinity of 3 over n? 0. And I get 7 over 2, which is 3.5, which is what we thought it was when we looked on the calculator, right? So sometimes the calculator is going to make it where you can see. Now some of us, though, were guessing with the calculator it was going to go to 4 because it was increasing. So if you don't go out far enough, you might not actually get the right answer with the calculator. This is going to guarantee you get the right answer. Okay? Alright. Here is our next one. Okay? So I've got limit as x approaches infinity of x minus 3x squared over 4x squared plus 3. What do I need to divide everything by? An x squared. So that means I will get limit as x approaches infinity of 1 over x minus 3 over 4 plus 3 over x squared. What does anything with a variable in the denominator become? 0, right? This is going to get 1 over x gets closer and closer and closer and closer to 0 as x approaches infinity. 3 over x squared also gets closer and closer and closer and closer to 0. So I end up with 0 minus 3 over 4 plus 0 when I take those limits, and I get negative 3 over 4. So this equation actually is going to get closer and closer and closer and closer to negative 3/4, negative 0.75. Okay. Questions on number 2? All right, let's look at 3. The book does this a little bit to you as well. They're wanting you to find the limit as x approaches, actually this again should say n, I messed that up. N approaches infinity of a sub n, but they don't give you the equation this time, they give you a chart. So you've got to find the equation. So, we're looking for a pattern. It might help us right here to make that 2 over 1. Because it looks like we've got a numerator and a denominator here that something's happening to. Add 1 to the numerator, right? So our numerator, so our a sub n would be n plus 1 in the numerator. And what about the denominator? N squared. Right? So we are finding the limit as n approaches infinity of n plus 1 over n squared. What would we divide everything by? N squared. So we'll divide by n squared, divide by n squared, divide by n squared. So that would give us the limit as n approaches infinity of 1 over n plus 1 over n squared divided by just 1, right? Okay, so we've got n's in the denominator of both things in the numerator, right? 1 over n and 1 over n squared. Both of those are going to have limits of 0. So 0 plus 0. And then what's the limit as n approaches infinity of 1? 1. And so what do we get? 0 over 1, which is 0. So this limit here would be 0. Questions? Okay. Here's our next one. Now, make sure when you're doing these problems, you're dividing by the highest exponent from the denominator. So what do we divide by here? X. Not the x squared, because it's whatever comes from the denominator. If you divide by the x squared, it's going to give you like a more complicated answer. So divide by the highest exponent from the denominator. So we're going to divide everything by x, which means we'll have the limit as x approaches infinity of 3 over x plus 4 minus x over 2. Now this one's a little different than the ones we've done so far, because we got that x, right? So what's the limit as x approaches infinity of 3 over x? It is 0. What's the limit as x approaches infinity of 4? What's the limit as x approaches infinity of x? It's not going to be 0 this time because 0 is not in the denominator. So, like, if you think of x getting closer and closer to infinity, this is going to be 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9. It's just going to keep on going forever, right? So, this is infinity. So, if it's in the numerator, it's just replaced with infinity. And then the denominator would be 2. So, we end up with 4 minus infinity over 2. What is 4 minus infinity? Does 4 even compare to infinity? 4 is going to be overcome by infinity, right? So it doesn't really matter what number you start at. If you subtract infinity from it, you're going to get negative infinity. If that was a plus infinity, we'd get positive infinity. And then what about if we divide negative infinity by 2? It's still negative infinity. So our answer for this, x approaches infinity of this 3 plus 4x minus x squared over 2x, is negative infinity. Or, now earlier Dylan asked the question about how can infinity be a limit? Negative infinity is not a limit, right? You're not going to go down the highway and see a speed limit sign that says speed limit negative infinity, right? So negative infinity is what this approaches. This means that this equation just gets more and more and more and more and more negative without bound forever. But that's not really a limit because infinity is not a limit. So sometimes you'll see, instead of negative infinity, you'll see does not exist. Okay? So whenever you get positive infinity or negative infinity as the answer, sometimes it'll be multiple choice. Sometimes they'll have that as the answer, the infinity or negative infinity, but at other times it may say does not exist, because that's technically not a limit. Now, all of these questions, the last 4 that we did, I knew the answer immediately before I even worked out the problem, and not because I remembered the problem. I know a shortcut that I can tell you the answer to all of these automatically. So let me tell you this shortcut. On the next slide, you see these weird letters down the side. And this is what we call our Bobo Botno eats DC. It helps us remember our limits as x approaches infinity. So Bobo stands for bigger on bottom. And that O right there is your 0. So if your exponent is bigger on the bottom, so that would be like example 3 there. Example 3, our exponent was bigger on the bottom, right? We had an n on top, we had an n squared on bottom. So if your exponent is bigger on the bottom, the limit is always 0. Okay? If it's bigger on top, not 1. Which means limit does not exist. Which means positive infinity or negative infinity. Now the reason I taught, instead of just going straight to the shortcut, the reason I had to teach you that other stuff is because on this part, sometimes you need to know whether or not it's positive infinity or negative infinity. And you can only do that by working it out like we did before. So this one, to know positive infinity or negative infinity, you do have to work out the problem. But we know if we have a bigger exponent on top, like example 4, where we had an x squared in the numerator and only an x in the denominator, then that's either going to go to positive infinity or negative infinity. And then the last one is exponents are the same, divide coefficients. So if your exponents are the same on top and bottom, you can just divide the coefficients. So if you look at number 1, you had a 7n squared and a 2n squared. So 7 divided by 2 gave you 3.5. That was our answer, right? For number 2, you have your negative 3x squared and your positive 4x squared. So negative 3 divided by 4 is going to give you the negative 3/4 is your answer. So this, you can use this to help you answer any limit as x approaches infinity problem. So let me look. We didn't get to the last couple of slides, which we will look at tomorrow, but you can do most of the homework assignment I have for you. So let me look at that real quick. Page 781. We're going to do 14 through 23 and 31 through 37. And tomorrow we'll do that second part. We didn't get to the problem today that I think is really cool, but we'll do it tomorrow. Remember, tomorrow is your stuff is due for your log module that you got to do. We will take our quiz on the logs tomorrow